Welcome to The Explainer. Today, we're going to dive into a real masterclass in engineering. We're talking about the high-voltage electrical system for one of the toughest vehicles on the entire planet, a hybrid cement mixer.
All right, so here's the plan. We're going to follow the complete engineering journey from start to finish. We'll begin with global regulations, get into the nitty-gritty of extreme loads, and go all the way to final validation to see exactly how you build the nearly indestructible nervous system for an absolute electric giant.
First things first, we have to start with the foundation, the laws. See, when you're engineering for a global market, you can't just pick one standard and call it a day. You have to satisfy the absolute strictest rules from every single region.
Now, this is where it gets really interesting. Each region has its own obsession, its own biggest fear. Europe is all about system-level safety and preventing thermal events. China draws a hard line on material properties and water protection. North America is focused on electromagnetic interference and what happens after a crash. And Japan? They demand incredible, long-term durability against constant vibration. So you're forced into this most stringent overlay approach, where your design has to pass everyone's toughest test.
And this slide just perfectly illustrates why you can't just borrow parts from a passenger car. A car designer assumes there are clean, dry places to put things. On a cement mixer, forget about it. There's literally no such thing as a clean installation zone. A car might get washed once in a while. This truck gets a daily, high-pressure, high-temperature acid bath. And its life isn't measured in years, it's measured in at least 15,000 hours of just brutal, non-stop work.
So what's the big takeaway here? The rulebook itself forces you to think differently from day one. You start with Europe's safety framework as your base. Then you use China's tough material standards as the minimum entry ticket for any supplier who wants to work with you. And the very first rule of picking parts is simple. If it was only ever designed for a passenger car, it's out. Immediately disqualified.
Okay, so with our rulebook firmly in place, now we can get to the physics of it all. How on earth do you size the wires and connectors that have to handle the insane amount of power it takes to turn a drum that's full of wet concrete?
Let's just pause on this number for a second. The main drive motor alone can pull nearly 450 amps. That is a huge amount of electrical current. It demands components that are just incredibly robust, able to handle massive amounts of heat and stress day in and day out without ever failing. So you can't just pull a number from a textbook chart. It's way more complicated. The whole process involves what's called derating for real-world conditions. You have to account for the fact that wires bundled together trap heat, or that they might be running through a part of the engine bay that's a scorching 105 degrees Celsius. You even have to factor in the effects of 15 years of aging and constant vibration. You have to design the system to be safe on its very last day of service, not just its first.
And the material you choose for the wire's insulation is absolutely critical. It's a constant trade-off. For the long cable runs along the chassis, the ones getting blasted by gravel, you use something called XLPE. It's incredibly tough. But right at the motor, where there's a ton of vibration and you need to make tight bends, you need super flexible silicone. But here's the catch. It's so soft that it needs its own protective braided sleeve just to survive.
The philosophy here is just be relentlessly conservative. You always calculate for the absolute worst-case scenario, you reject any new fancy connector and stick with ones that have at least 5 years of proven real-world use in other heavy trucks, and you mandate the best materials, like silver plating on all the high-current terminals, because that prevents the kind of corrosion that can lead to catastrophic overheating. You design for the worst day, not the average day.
All right, now we have to talk about an enemy you can't even see. This truck has two incredibly powerful inverters, and they create a massive storm of electrical noise. If you don't shield everything perfectly, that noise can actually cripple the truck's critical 24-volt control systems.
Okay, this is a super common point of confusion, even for experienced engineers, so it's worth clarifying. You have two different kinds of grounds. The cable's braided shield is for high-frequency noise. The best analogy is a soundproof drum. For it to work, it has to be completely sealed, connected to the chassis at both ends. The safety ground, on the other hand, is a totally separate wire. Its only job is to protect people from electric shock during a fault. It's like the third prong on your toaster's plug.
And the lead engineer on this project? Well, they don't mince words. The techniques that might work in a passenger car, like grounding a shield at only one end, are absolutely forbidden here. For a system this powerful, it's just a guaranteed recipe for failure.
So we've handled the invisible electrical threats. Now let's talk about the very visible, very physical ones. The system has to survive in a brutal environment that the engineers literally call the concrete jungle.
First up, the chemical attack. At the end of every single workday, the crew has to get hardened concrete off the truck. How do they do it? With hydrochloric acid. That means every external connector, every cable, every bracket has to be designed to resist being bathed in strong acid, daily.
Next is the constant physical assault. Any wire that's routed underneath the chassis is basically in a war zone. It's being constantly pelted by gravel and rocks kicked up from the tires. This isn't just abrasion resistance. We're talking about needing what is effectively armor plating.
And finally, there's the daily cleaning. And look, we are not talking about a gentle car wash. This is a high-pressure water jet heated to 80 degrees Celsius, aimed at every component from point-blank range. This brutal test is called IP6K9K, and it's the highest possible rating for vehicle water protection for a reason.
So the big lesson here is that you can't just trust a lab report. Your design has to be clever. You have to incorporate simple but effective mechanical tricks like a drip loop, which just uses gravity to guide water away from a connector seal. And you have to validate your parts with some pretty brutal, real-world tests, like literally letting concrete harden around them and then smashing it off to see if they survive.
Okay, so the system is physically tough. It can survive acid, rocks, and water jets. Now we need to build the fortress of safety around it to protect the operators and technicians.
The magic behind this is a system called the High Voltage Interlock, or HVIL, and it's actually brilliantly simple. It's just a low-voltage circuit that runs through every single high-voltage connector. The trick is, the pins for this circuit are shorter than the main power pins, so if someone tries to unplug a connector, the HVIL circuit breaks first. It's like a tripwire. The instant it breaks, it tells the vehicle's control unit to cut the 400-volt power completely, all before the main power pins have a chance to separate. This prevents a deadly high-voltage electric arc.
And finally, after all of this design theory, all of the calculations and material choices, everything has to be proven. The system now enters the final gauntlet, a validation plan so comprehensive it separates a truly robust design from a future liability.
And this right here is what separates professional-grade testing from the basics. You don't just do tests in isolation. The tests are done in sequence to make them harder. First, you shake a component on a vibration table for days to simulate years of driving on rough roads. Then, you artificially age it by subjecting it to hundreds of extreme temperature swings. And only then, after it's been shaken and aged and weakened, do you blast it with that high-pressure water jet to see if the seals can still hold up.
So it all comes down to this really important difference between DV, design verification, which asks, is our design good on paper? And PV, product verification, which asks, can we actually build this thing reliably 1,000 times? And it all culminates in one final ironclad rule. If the complete, fully assembled truck cannot pass that final water torture test, it does not ship. No exceptions, period.
So after this deep dive, you really get a sense of the incredible level of engineering that goes into these industrial EVs. And it leaves you with a final thought, right? If we're learning how to build electric systems that can survive this kind of unimaginable abuse, what lessons can we take from that and apply back to our everyday cars to make them last longer, be more reliable, and ultimately a lot more sustainable?